Right, thank you, Dr. Reed. Thank you all for coming today. I really appreciate that you're here so early this morning to witness our System of Systems validation review. So today we'll be talking about our Rogue One mission, and I would like to first introduce our overview, which we're going to go through our mission summary, concept of operations, our mission history and systems history, our System of Systems definition, our configuration management examples, some of our mission results, and finally our ground system validation. Today joining me are Assistant Project Manager Gino Ferra, Invictus Representative Jonathan Hamburger, and Endeavor Aerospace Representative Michael Fusco. Now, the following diagram depicts our design team layout. As you can see, we have a project manager and assistant project manager alongside two design teams, which are Invictus and Endeavor Aerospace. Each one of these teams is led by their respective principal investigator, and along all of us, we have our system integration team. As mentioned in the introduction, our mission is a Rogue One mission, which stands for our Reconnaissance Operation for Guided Unmanned Exploration 1. Our mission purpose is to develop an unmanned aerial vehicle that will transport a reconnaissance vehicle to a remote location. It will survey it, then return to the aerial vehicle, and then we'll both together return to the starting location. For our mission, there are three corresponding systems. It's the ground station system that we'll be talking about today during this presentation. We have our Vesta system, which is our hexacopter over here on my right. This system will be covered at 9:15 today. And finally, we have our Aura system, which is our rover, also here on my right. And we will be covering this system at around 10:15 a.m. Right. The following diagram depicts our system architecture of the ground station system. As I mentioned earlier, we'll be talking about this system during this presentation. This is just a diagram that depicts the components that comprise this ground station system, allowing us to communicate with both vehicles. We also have our latest conceptual design for Vesta system, the hexacopter, and the Aura system, which is on my left here. For our mission, we have developed 8 primary objectives that dictate the progress of our mission and the progress that we have to take within our vehicles. Starting with the Aura and Vesta system should be initiated at the center of the Mos Eisley spaceport that we refer to as the location where both vehicles will start the mission. Our Vesta system, our hexacopter, should transport the Aura system to the Yavin 4 ruins, which we refer to as our operations area. At this point, I hope you're all familiar with these terms. We are very fans for Star Wars, so we adopted a lot of their names. So our third objective is that the Aura system should be deployed after the Vesta system has landed in an approved landing area. The Aura system should navigate the operations area. The Aura system should generate detailed images, transmit the visual data to the ground station, and then return to the Vesta system after this data has been transmitted. Finally, we have our Vesta system that should transport the Aura system back to the starting location after the Aura system has returned to it. We also have 4 constraints for our project that dictate us the limits that we have within our project. For example, we have that our cost will be less than or equal to $3,800, a total mission duration less than or equal to 60 minutes. The Vesta system will land in a grassy portion of the operations area, and the Aura system will only navigate that grassy portion in the operations area. Now, I would like to introduce you to our concept of operations. This is a simulation that we have developed to represent the progress of our mission, starting with phase 1, our pre-flight phase. During this phase, we'll have all of our systems. Could you play the video, please? Thank you. So we have our locations that I just described. Our ground station will be located here in the conference room in this building. At this point is where we set up all the equipment that belongs to the ground station and that will allow us to communicate with our vehicles. The Mos Eisley spaceport, as I mentioned, is where both vehicles will be set up and they will be starting the mission. Our Yavin 4 ruins is the operations area that the Aura vehicle has to transmit video from. And we have this hyperlink that will be marked here with 2 lines that depicts the bounds that the Vesta system has to flight within. Moving on, we have our phase 2 of our concept of operations, the transport to Yavin 4 ruins. In this phase, the Vesta system takes off from the starting location while carrying the Aura system, and they will navigate or fly through the hyperlane that was just mentioned to land and softly land. I should emphasize on that. Softly land so that it can deploy then the Aura system. Phase 3 is the deployment of ORA. Through these our safety mechanisms, there is a setup of servo motors with the foam blocks that lock the ORA system in place. They will be released, and then the ORA system can drive out of the payload bay. Our Phase 4 is the reconnaissance of the Yavin ruins. This is just a simple area that we reconnoit, and while transmitting visual data, we have a camera mounted on the rover that will be providing the visual images for the operator to manually navigate the operations area. Once it's done, it can find objects of interest that we're interested in. In Phase 5 is the reverse process of Phase 3. It just has to dock with Vesta again by driving up the payload bay in the Vesta system, and then will be locked into place with the same mechanism in reverse. The servo motors will just lock in place to hold Vesta system, the ORA system during flight. Phase 6 is a reverse process of Phase 2 is a return to the starting location. Through the same hyperlane, the Vesta system will perform a second flight to bring back the ORA system to the starting location. Also, it will finish with a soft landing. And finally, our Phase 7 is our post-flight phase. At this point, we disassemble all the systems, we're done with our mission, and we're ready to analyze the data. Now, our mission history. During this following slides, I'll be presenting you with some changes that we had to perform to our mission due to setbacks, issues, or problems that we encountered during our project. For example, our first two objectives that I presented a minute ago that dictate the location that we're going to use for our operations area and our starting location had to be modified due to the following reasons that I will take you through. For example, our mission location 1 is very similar to what we ended up doing, with the exception that we planned for this location for 28 weeks. We designed our system to take off from this area to land in this enclosure, and then that we will be reconnoitering. Unfortunately, the facilities department denies the use of this enclosure due to concerns for damaging their equipment. And again, I would like to emphasize that we designed for 28 weeks our project for our vehicles to operate within those bounds, and we were not able to use it. So we came up with other suggestions and other proposals, such as mission location 2, which is also within campus enclosures. We have our new landing site and our new starting location in the Spurance house. This is a house that is available for guests in the university. Unfortunately, due to the frequent use of this house, the safety department was also uneasy of letting us use this location. So we had to come up with a third possibility, which is R4, also within campus enclosures. This is a storage location that they use for facilities as well. This was a perfect area, also it's next to the house of the Chancellor. We have a pretty good view of our vehicles. This was a perfect location. Unfortunately, our ground station system was designed to communicate at the initial area that I just presented, but for this location, it couldn't secure a link for connection with our vehicles. So we were forced to move again with our location. Location 4 was in the soccer field. We had, again, a proposed takeoff and landing area, and unfortunately, we were not authorized by the athletics department to use this location. I should mention that, as you can see, all of these locations are within their campus enclosure. Our decision for these locations were that we wouldn't like to be liable for any damages or any sort of damages to people or something like that if we were to perform our mission outside of campus. So we stick to locations that we could use within campus. So our final location that we decided to use was exactly, well, almost exactly as the first one, where we have our ground station system here and our takeoff area exactly as originally intended. And we just pushed the landing area over here to this side that was a public available area for us to use. Now, our systems also have their own history. For our vehicles, mainly, we went through a series of modifications and changes that we had to perform due to testing, analysis, and simulations that we came up with to solve problems that we encountered. So, for example, beginning with Vesta system, the hexacopter, it started being this on version 1, our very first CAD model of the Vesta system. It was an octocopter that was just capable of taking off and carrying the ORA system. Version 2, we decided to select for selection of electric motors and propellers for our propulsion system, and we also have payload bay for ORA system. Version 3 focused on designing an accessible payload bay for the ORA system. Version 4 refined the aerial structure and the landing legs. Version 5 went from an octocopter to a hexacopter and focused on a closed shape for the aerial structure and also a lightweight payload bay for Vesta for the ERAU system. Version 6 focused on the weight problem, so we went with a carbon fiber layout for the structure, and we replaced the payload bay with a set of hooks that would be able to engage the ERAU system in. Version 7 and 8 come closer to our final product, where we settled down in a decision designed for a payload bay and the electronic equipment layout in both cases. Version 8 presents the final selection for the set of electric motors and propellers in our CAD model, and version 10 added a couple of other components for a flight controller, a Pixhawk, and a GPS module. And finally, our version 11 is our final CAD model for our Vesta system, and as you can see, we also added a couple of struts in the T-beam arms and holes in the aerial structure to reduce weight and provide stability to our vehicle. We also have some changes for our rover or ERAU system. In version 1, we have our very first CAD model for our rover. It just consisted of a 4-wheel rover equipped with a camera capable of transmitting the visual images. Version 2 has a different physical structure and setting down in wheels and stepper motors for our traction. Version 3 focused on the layout of the electric equipment, and as you can see, we have a modem and an antenna for the communications that were later replaced in version 4 with a more powerful antenna and a more lightweight modem. And finally, we have version 5 and 6 that are just very similar, where we settle down in the camera decision and some weight reduction in our physical structure. Now, for a system of systems definition, the following diagram is our design structure tree, which presents the solution that we have developed to satisfy all of our system requirements and objectives. As you can see, we have all 3 systems at the top, the Vesta, ERAU, and the ground station system. Today we'll be talking during this presentation about the ground station. And each one of these systems has its own respective subsystems and components. Now this, again, is a diagram for the ground station system architecture. It's a series of components that allow us to communicate with both vehicles. And this is a diagram with the actual components that were purchased to successfully validate those requirements. Now, as a comparison, I presented you our final CAD models for each one of the vehicles, the Vesta on the left and the ERAU on the right. And then the following picture is a comparison with our final products that were fully fabricated and assembled. We also have them here on our table, so if you want to inspect them a little bit more in detail, we can do so at the end of this presentation. Now I'd like to pass it on to my colleague Gino Ferrer to talk about our configuration management.
Thank you, Manfred. Shown here is our product structure tree. The product structure tree shows how all of our systems were designed and assembled from the bottom upwards. Each box here represents a sub-assembly. All of these sub-assemblies have 2 partitions, one being the bill of materials and an assembly drawing. A bill of materials is a list of all parts used within that sub-assembly, and an assembly drawing shows how those parts are fit together. Shown here is an example of part of our assembly drawing for the Vesta system. This shows how the electronic speed controllers were attached and where they were attached to the Vesta system. Here's its corresponding bill of materials. Each part here has a part number, part name, and quantity assigned to it. It should be noted that some of these parts have additional flavors assigned to them. These flavors are used to denote parts of slight variances, such as an Ethernet cable with slightly different lengths. Here's another example of an assembly drawing. This is an assembly drawing of the Vesta system. This shows how the wheels were attached to the Vesta system, and here's its corresponding bill of materials. Here is a part drawing. We have over 150 parts within both systems. This is the axis panel for the ERAU system. It's what fits on top of it. Now I would like to go over some mission results. Here is one of the system tests for the ERAU system. The ERAU system leaves the payload bay of the Vesta system and then heads towards the Mos Eisley spaceport. Once it has reached the Mos Eisley spaceport, it would then look for objects of interest. It should be noted that this video is at 16 times speed. Once it has found those objects of interest, it can then return to the payload bay of the Vesta system. redock. Here's one of Vesta's first VTOL tests. In this video, Vesta lifts off the ground to its required height, and then after about 30 seconds of hovering, it safely returns to the ground. Next, we have Vesta's crash. Unfortunately, last Friday, Vesta, don't play it yet, please. Unfortunately, Vesta lifted off very quickly. After a matter of seconds, it became unstable and crashed to the ground. Now, please play it. Since this happened last weekend, we did not have enough time to rebuild and retest, so we had to move forward with analyzing this. This will be covered in more depth during Vesta's presentation at 9:15. I would now like to hand it off to Jonathan Hamburger to discuss the ground station system.
Thank you, Gina. Shown is the ground station design structure tree. It is comprised of 3 subsystems, Aura Command, Comms, and Vesta Command, and its respective components. In this presentation, we'll be going over system level and subsystem level validations. The ground station system has 3 primary objectives. It should provide an operational platform to remotely conduct the mission, and it should collect and save broadcasted visual data of the Ad4 rooms. The constraint for the ground station system is that it should be located in the executive conference room of this building, Academic Complex 1, or AC1. This is the design solution that we have generated to satisfy these objectives. Note that we have 3 clients or computers that are able to access the modem, which serves as an access point to the network that was utilized for this mission. We were able to experimentally satisfy the objectives of this ground station during the Aura system testing. So this is a picture of the ground station during the Aura system testing. Shown are the 3 computers of the ground station. Note that we are in a remote location, the executive conference room of this building. And if you look at the center computer, the streaming computer, we have a live feed of the video stream from the Aura system, and we were saving it to that computer. Thus, we were able to satisfy the objectives of the ground station system. Moving on to the Vesta Command subsystem validation, shown as the Vesta Command subsystem on the design structure tree. There are 2 primary objectives for the Vesta Command subsystem. It should provide an operational platform for sequencing data input, and it should display sensor data. The 2 constraints for our subsystem is that it should use Secure Socket Shell Protocol, or SSH protocol, to remote access into the Vesta system, and it should connect to the communication subsystem via Ethernet. Shown is the simplified design solution for this subsystem. Note that the Vesta Command subsystem is comprised of a computer with a user interface. Also shown on the diagram is the network traffic and its direction between the Vesta Command subsystem and the Vesta system. So the Vesta Command's computer has a user interface that accepts sequencing data input that's sent to the Vesta system, and the Vesta system sends sensor data to the Vesta Command computer. Sequencing data refers to data that's sent to the Vesta system that initiates autonomous flight or the servo docking mechanism. So an example of this is shown. We were able to SSH into the Vesta system, and we're able to run a program that accepted inputs for the servo docking mechanism and had the vehicle respond to it. Similarly, with the same connection, we were able to run a sensor program that displayed the sensor data and output of the Vesta system. Thus, we were able to satisfy the objectives of this subsystem. Moving on to the Aura Command subsystem. Shown is the Aura Command subsystem on the design structure tree. There are 4 primary objectives for the Aura Command subsystem. It should display visual data. It should save that image data broadcasted by the Aura system. It should display sensor data, and it should provide an operational platform for command data input. The 2 constraints for this subsystem is that it should use SSH protocol to remote access into the Aura system, and it should connect to the communication subsystem via Ethernet. Again, we have a simplified design solution that shows the Aura Command subsystem and the Aura system and the network traffic between and its direction. The Aura Command subsystem is comprised of 2 computers. The Aura Command computer, which displays the sensor data of the Aura system and has a user interface for command data inputs. This allows the operator to manually control the Aura system during the mission. And then we have a streaming computer that shows the visual data stream from the Aura system so that the operator can navigate the vehicle. An example of the streaming computer is shown. So the Aura the Aura system camera has, it comes with a program called GeoVision, and that manually, that displays that video feed for us. To access GeoVision, you simply you open Internet Explorer, type in the IP address of the camera, and that'll pull open this page that shows the video feed from the Aura system. To save that video feed, we used an application called Windows Gaming Bar, which records a video, and later we could go frame by frame to get individual photos from it. We have an example of the sensor display of the Aura system. So similar to the Vesta system, we were able to SSH into the Aura system and run a sensor program. So this displayed the sensor data of the Aura system and continuously updated until it was terminated by user input. And then we also were able to run a program that accepted user input. This program accepted translation, rotation, throttle, and stepper count, which was sent to the stepper motors on the Aura system and was used to maneuver the vehicle. So in summary, all of the objectives for the Aura Command subsystem were satisfied. And now I'd like to welcome up Michael Fusco to talk about the communication subsystem.
Thank you, Jonathan. The communication subsystem is shown on the design structure tree. It has 4 components: an antenna, a network switch, a modem, and a power over Ethernet or PoE box. There are 5 objectives for this subsystem, including that it should receive visual and sensor data from the Aura system, should transmit command data to the Aura system, should receive visual data from the Vesta system, and should transmit sequencing data to the Vesta system. There are 3 constraints, including that it will transmit and receive data on non-licensed or consumer frequencies, and will establish a wireless local area network. There are 5 requirements for the subsystem, including that it shall transmit with the bit error rate less than 0.01%, shall be capable of transmitting a data rate greater than or equal to 0.7 megabits per second. The subsystem shall be capable of transmitting and receiving data over a line of sight distance greater than or equal to 215 meters. And finally, the subsystem shall be capable of transmitting data with an equivalent isotropically radiated power, or EIRP, greater than 35 decibel milliwatts, or dBm. Shown here is the network switch component selection. It has 5 data input-output Ethernet ports, which allow for the 3 clients of the ground station system to connect to the modem component. The network switch handles network traffic on the network. The power over Ethernet box takes an input from the switch component and injects into the line 24 volts to power the modem component, shown here. That Ethernet line is taken in on the left and connects to an antenna on the right through an N-type connector. The modem serves to modulate and demodulate network signals for transmission and reception, and when combined with the antenna, creates an access point to the WLAN. The selected component through Ubiquiti Networks has a transmission power of 28 dBm. The antenna selection is a panel antenna which provides for directionality and therefore has a large gain of 11.1 dBi. Shown here is the communications network configuration for the system of systems, with the ground station shown on the left. The access point of the ground station can connect to the access points created by the modem antenna combinations on the vehicles. The feature of this network is that we can connect either directly to the vehicles, or we can use one of the vehicles as a relay to the ground station, which is particularly useful for when ORA performs the reconnaissance mission. In order to numerically validate the requirements, we performed a network performance test. We first set up an access point of the vehicle 215 meters away from the ground station location, which was on the roof of this building due to scheduling constraints with the conference room. We used a software called ERAU-OS, which comes with the modem in order to determine signal parameters, including frequency, bandwidth, transmission power, signal strength, and noise floor. This table lists the properties of the network that we established. We use wireless protocol 802.11, which is Wi-Fi, N-type, which had a center frequency of 2,444 megahertz and a bandwidth of 20 megahertz. The modulation type was 64-bit quadrature amplitude modulation, or QAM, which corresponds to a data bandwidth of 8.1 megabits per second. As you can see from the table on the top, the bit error rate requirement of less than 0.01% was both numerically and experimentally validated. The bit error rate is a measure of signal fidelity on the percentage of transmitted bits being lost. You can relate the bit error rate to the carrier to noise ratio, or CNR, through a white noise model. And that's how the results for the bit error rate were generated. In order to validate the data rate requirement of 0.7 megabits per second, we calculated our CNR to be 27.2 dB, which was greater than the required 21.6 to deliver our network performance. Therefore, we assumed that we could deliver the full data bandwidth of 8.1 megabits per second. Experimentally, we were able to transmit a maximum of 2.56 megabits per second, and thus both numerically and experimentally validating this requirement. The line of sight distance requirement was also validated through the carrier to noise ratio calculation. We used the required 215 meters in calculating CNR, and also found it was greater than the required CNR for bit error rate. In practice, we found that the experimental CNR was 28 dB, and we suspect that it's slightly larger because we used a conservative estimate for loss in calculating CNR. So with the experimental CNR, we are able to correlate that to a 700 meter transmission reception distance. Finally, the requirement associated with EIRP was numerically and experimentally validated. EIRP is the transmission power plus the gain of the antenna. And the numerical result is greater because the specification sheet for the modem listed 28 dBm, and that was for BG type wireless protocol. However, we used N-type, which had a maximum transmission power of 25 dBm. So it was less, but it still met the required 35 dBm. So in summary, all 5 requirements were both numerically and experimentally validated. And now I will show a video that demonstrates the Objectives for the communication subsystem corresponding to the ORA system were satisfied. This video will show the ORA system undocking from the Vesta system, and the video stream was received at the ground station remotely, and a user commanded the vehicle out of the Vesta system. And Benedict will begin the video. At several points in this video, you may see that it pauses. This is due to the fact that the operator stopped the vehicle to make maneuver decisions. It is not a result of the video stream being interrupted. The speed is 1.5 times. This time I'd like to hand it back to Manfred to conclude the presentation with programmatics.
Thanks, Michael. Well, to conclude, as I mentioned in the introduction, our project consisted of a total budget of $3,800, and here listed is our projected cost analysis and our total cost that was associated to our components. We had a remaining budget of $460, so we came pretty good in our budget. For our ground station system, the outline is here listed for our component selection, the projected cost and the total spent, and we also came under budget in this system. In total, our team, which is the combination of both vehicles in the ground station, has worked a total of 10,298 hours, not dollars, ever since the beginning of our project in August 28th of last semester. So this was a total time that took us to develop both systems from preliminary design to our class day. As you can see the diagram, we have the different categories for our classification of hours. We had engineering, we had professional development, which was hours spent during class time. Our management, engineering, technical, and administrative hours were hours worked outside of class by all team members. In engineering, like for example, the technical aspect of our paper calculations, our paper design, and the technical hours being actually fabricating and assembling our components. And finally, we had some teammates that worked on during projects. So in summary, we have some lessons learned. For example, being our logistics of project development, as I mentioned, of our changes in mission location. We had to learn how to foresee those changes after the first one happened. So we came up with a lot of proposals in case a lot of them were canceled or denied as it actually happened. We also learned how to communicate the design changes to our customer. As Dr. Benavides mentioned in the beginning, we take this project in a systems engineering approach. So we couldn't make decisions or design changes at free will. We had to communicate them with our customer, which was our course instructor, and we had to negotiate with him the design changes that came up upon testing, analysis, or other problems. And finally, we had to prepare for changes that were out of our control, referring to this point as the Vesta crash. We definitely learned from that we didn't have enough time to complete and successfully meet all of our mission objectives. As you saw in the video, the Vesta system crashed, so we couldn't completely satisfy our mission objectives. And finally, we would like to acknowledge the following people, being especially Dr. Julio Benavides and Dr. Matthew Haslam, our course instructors, and especially the people joining us today from the panel. And now I would like to join with my colleagues and open the floor for questions if you have any.
We have 25 minutes.
Probably or do maybe one question down the panel, and if we have extra time, we can ask some more questions. That will be good. ahead.
So, when you had to change locations a bunch, did you already have different locations in mind, or was that something that you had to think of after the first one didn't pan out?
Right, so like I mentioned, we planned for first location for 28 weeks. That was like 3/4 within our project development. So after the first one changed, we were fairly confident that we could get it to the second location. But then it was denied, then we came up with a list of possible locations that we could use, and then we implemented them. And all of them got denied, so we ended up with our final.
First, I just want to say congratulations. This was a really ambitious undertaking, and I'm really impressed you were able to pull it off in the time frame that you were given. My question pertains to the communications integration between Aura and Vesta. You've noted that both systems communicate directly with the ground station. I'm curious if there was ever any consideration between using the Vesta system as a communications relay between Aura and the ground station, and if that was on the table, why it wasn't considered?
Right, that's a very good question. We actually expected that, so I will pass it on to my colleague Michael to talk about that.
Yeah, it was implemented, as you said, in that it was set up to relay data. So the Aura system could transmit data through the Vesta system, so long as the Vesta system had line of sight with the ground station.
Okay, I apologize. I misunderstood. My understanding was that Aura was communicating directly with the ground stations.
It has the capability to.
Okay, so it's dual capable. is what-
Yes.
Okay. That's impressive. Thank you.
Okay, great job on an ambitious project. Question, what caused the instability and what would you do to fix it?
Right, we actually have our principal investigator for Invictus that's joining us today, and he was in charge of the development of our Vesta system, so I will let him explain to you a little bit in further detail the mishaps that happened with the Vesta system.
Thank you, Manfred. So firstly, we're going to go into a lot of detail with that in our next presentation, but to give a brief overview, we think that something that had a large effect on it was that the PIXHawk 2.1 does not allow input of the inertia tensor. So it didn't have an accurate understanding of what the vehicle dynamics were. All we were allowed to input was that it was a hexcopter configuration, so 6 motors and then what the symmetry of the system was, and that was provided as an ability for, through the PIXHawk 2.1.
So some asymmetry associated with the operation of the motors?
Less the motors and more the structures of the system. There were 6 batteries and 1 component battery, as well as the modem and antenna. Due to some constraints we had as to where things could be placed, we did have some asymmetry in the design of the system, and we were hoping that the PIXHawk 2.1 could correct for it. And unfortunately, we think that that is an effect as to why it was unable to remain stable. But we do have stable flight tests that we will also share later today.
Thank you.
Thank you.
If I may add to that a little bit more, we actually got to understand that the PIXHawk system that we use for control is very robust. In one of our tests during a vertical takeoff and landing, we actually happened to have a motor disconnected, so the PIXHawk actually managed to stabilize itself and land, not perfectly, but it was stable enough so that it wouldn't break entirely. But in this case, our mishap was something different, and it caused us to get.
You demonstrated one motor out.
Yes, well, it was not planned for, but But when we came to inspect the vehicle, we realized that one of the ports where you connected electric motor was disconnected. And we have a video for that, but I think Benedict will present it. I don't know, and you can see as it goes a little bit unstable, and then it lands.
Good job, guys. That was it was a really good presentation and clearly a lot of work that you've done. I have a lot of questions, so I'll start with configuration management. So I saw you guys had assembly drawings, and I mean, from a kind of a bird's eye view, they look very good and professional. Did you guys have any integration or interface control drawings between Vesta and Aura? And then, do you have any lessons learned or issues that you went through in developing those assembly drawings versus actually integrating the hardware?
So as for the first question, we don't have many views of the systems integrating together because it just drives into the payload bay. But if you open the first assembly drawing for the Rogue One system, on the next page there are examples of how exactly it fits together.
So if you build the Aura and Vesta to spec, then the integration together, it was assumed that that would come together and work.
Yes, which it did.
We had a lot of communication among both teams, whether there was one team developing the hexcopter and another team developing the rover. We were in constant communication to remaining in the same page with our dimensions, our weight constraints, our current updates. We had a very, very good communication.
I love to hear that communication is very important. And keep in mind, in the professional world, when it's not just an in-house project, you have to define those interfaces because you're typically working with a different vendor who's providing the rover or so on. But communication is good.
Nice job. I have a couple of questions. First one was, for the bid error rate, why was the value of 0.01% chosen?
This was mainly after consulting our EE professor, Dr. Suleiman, and the main reason is that, well, it was mainly through consultation.
So I want to get to the system engineer aspect of it. So customers will often have requirements and provide values, and your job when you're designing and responding to those is to understand why they're coming at it. Because I certainly saw that you guys met all your requirements, but a lot of you had huge margins in some areas, like communication, bid error rates. So that's great, but then it makes you question, so understanding the intent and rationale for requirements is just as important as understanding the shell statement that's provided. So that's something to keep in mind. And then the other questions that I had was, were you able to characterize the difference between the 8.1 megabits per second and 2.5 megabits per second between the numerical and experimental communication values?
The 2.56 megabits per second was the maximum that we tested. We believe we could probably provide a greater data rate, which could be demonstrated through opening multiple network streams. But the 2.56 corresponds to the streaming 720p, which we're able to successfully do remotely.
So that's so thank you for answering that question. I understand why. So that's another point of kind of lesson learned there is when you're setting up your tests, make sure that you can set up your tests to get to the max capacity. So just a good point there, because that wasn't made clear that why was the numerical so different from the experimental. But just keep that in mind that your tests have to be accurate to be able to test and report data. Send it in this case. Thank you.
Thank you.
So you showed a lot of, and maybe we'll get to this in the next two presentations, but the Cad design from the little boxes to the kind of full fidelity. How much of that was chicken and how much was egg? Like, was it you designed it and then found the parts, or was it your design was then dictated by what was available in terms of capacity?
No, we developed our requirements and we designed to meet those requirements. So a lot of our design came up. We actually didn't fabricate anything until the last 4 weeks, I would say. So we had our full first semester developing this project in paper, and about half of this semester to continue developing. And a lot of this was just our paper and a design based on modeling and simulation. And we had to do a lot of calculations, especially with our communication subsystem. We had some, and this will be covered in further detail in the later presentations, but for the Vesta system we did thrust analysis and other simulations that took us to select our components to satisfy those requirements.
Right. And I'm a little confused as to the organization. You had two names on your org chart, and I see 5, 6 of you up there. Could you give us a little bit more information about what each person was in charge of?
Right, so we had two main teams designing each vehicle. I am the project manager. Gino here is our assistant project manager. Jonathan and Michael are representatives from each team that handle the communications aspect of their respective systems. But since both of those system communications are pertinent to our ground station, among all three systems, they took care of those communications aspect. So that's why they're joining us in this presentation today.
That was, sorry, what was your name again?
Michael.
I'm Michael. And John.
John.
And,
I'm Barrick. I'm the principal investigator of the rover team.
and then you're the principal investigator of the,
Yes.
okay,
Yes,
thank you.
ma'am.
Was confused as to what y'all did. How much of the work that was done autonomously, or was it all manually controlled in terms of the flight and the driving?
Right. So our hexacopter Vesta system, it was expected to receive command inputs from the ground station. Let's say it would receive a command to take off, and then that flight, the entire flight would be performed autonomously based on the systems implemented in the Vesta system. Then would receive another command, such as release the docking mechanism, and it would autonomously release the servo motors. So it would receive that sequence of commands and then perform the action or the activity autonomously. The rover was totally manual. The operator had at the ground station a screen, the streaming computer with the video feed coming from the camera, and it would have a command computer where it would input the commands for moving forward, moving right, moving left, and moving backwards.
Okay, and well, I would like to say I forgot to put this in, but it's a great job. I think it's very impressive. I have one nitpick, which is one of your requirements said to work within 215 meters or more. So it can, we can drive this thing from the moon. Like, I mean, there needs to be bounds on both sides. And it looks like you did some of your testing, or the planned driving, the takeoff spot was less than 215 meters just from the picture that you guys had. So obviously it had to work in less than 215 meters. So think about that next time.
Right. That actually relates a lot to the question that we had from Ole, Mr. Ole. Because we actually, as you said, we actually have to know why some of the requirements were developed. So at the beginning of our project, we were, like I said, not just thrown out there to design something at free will. We actually received an outline of the main aspects of what the mission had to do. So a lot of our mission objectives were provided to us, and one of those was to develop a system capable of operating at a minimum distance of 215 meters. So we stuck with that requirement for most part of the mission. And I would like to pass it on to Michael to add to that.
It also goes to the point of the data rate requirement. So the distance and the data rate both should have been bounded. The distance was not, or was set as greater than, and the data rate also greater than. But the 0.7 for the data rate was the minimum of the video stream that we wanted, 240p. So we didn't anticipate using up to 8.1 megabits per second. But yeah, that's a lesson learned too. Should have bounded the requirements.
Yeah, we have time for one more round.
Okay.
We have 8 minutes for Q&A.
Okay, I got it for you. Okay, so before the briefing I read ahead, on your abstract, I want to read part of it back. It says, Rogue One is a project developed by aerospace engineering students with a systems engineering approach allowing a clean and well-organized documentation for future reproduction. Wow. What exactly does that mean?
That's an excellent question. So we have, we're very proud of our documentation process of this project. As it's mentioned in the abstract, we actually plan to develop this project so that anyone can take over the documents and recreate them to this very last step, from our analysis, model and analysis, to our fabrication and assembly. And if Benedict, if you would like to see, we have examples of our procurement plans, assembly drawings, part drawings, our critical design document, which is our full paper design. So that's, for example, the procurement plan of component selection for each one of the systems. We also have for the ground station. This is a fabrication plan. This is a list of steps that you have to follow for assembling, alongside with the part drawings and the assembly drawings, each one of the systems. And verification plan, this was mainly for our course instructor to verify that we were actually doing what we were planning to do. And like I said in one of the other questions, sorry, I lost my point. Yeah, our documentation is planned for everyone to take over the documents and recreate these systems.
Good enough. Who else?
So in terms of documentation, systems engineering best practices, so what I'm missing, I saw all of your, the objectives, mission objectives, and I really liked the comm subsystem flow down showing the requirements and the validation of those. What about the other requirements? And so you mentioned documentation, assembly drawings, procedures, stuff like that. But what about the requirement documents?
Right, we also have our OCRs, objective constraints and requirements documents that outline all of those for each component, subsystem, system, and subsystems. That for each one of the vehicles. But we also have our critical design document, which is a full document of all three systems validating in paper, numerically validating our requirements. For our portion of this presentation, we don't have any system of systems requirements. We have the communications requirements, but in the other presentations, we'll be covering their system requirements and below.
Okay, that would probably would have been good to know for me right up front.
Okay. We'll take note of that.
A couple of observations as you figured out later on in your process. Regulatory considerations can be a nightmare, and they don't go away no matter what industry you go to in aerospace. And a lot of them that exist because of human safety, and then being foremost important, but also that property and your hardware safety being the second item that's important before even any of the mission objectives. And you can clearly see that industry right now with Boeing having troubles with their software and airplane, right? Grounded the entire fleet, huge disruptions to the air travel, implications on huge losses in cost and human lives. So just something to keep in mind that issue does not go away just because you're moving into the industry. The other item when we have is ground systems and comms and operations is definitely not usually the sexy part of the missions that we work on, but they're just as critical to mission success. So I hope you realize that, and hope some of you go into the ground systems and the ops area. I certainly got some work in that, and just keep in mind that's part of the larger picture of what we do in aerospace. And then the question I had was, there wasn't really discussion about procedures or so could you chat about maybe lessons learned about procedures that you've implemented and how you went about creating them?
Right. Well, first of all, thank you for your comments. Those are very good input for us. And do you refer to as our procedures for assembling, fabricating, or our mission procedures?
Your operational procedures.
Right. So we have developed our mission operation plan, which is also another document that dictates and presents all the personnel required. If there's going to be a flight director, a system director, or a system operator, and their responsibilities, their tasks, and we have a table with every single step that needs to happen in order to satisfy our mission objectives. From the very beginning of how to set up the ground station components to create the network, to how to operate the system, and finally how to navigate the vehicle. It would be the case for ORA. So we also have a procedure for the mission. And we created, additional to that, we created an emergencies procedure in case the Vesta system could caught up fire during flight, the rover could get stuck or something like that. And lastly, we had another logistics procedure, which was our process of documenting our mission that we didn't get to successfully do because we couldn't get a full system of systems flight, but we were able to document portions of it.
So one quick comment, all of these documents that you're talking about, that's fantastic. We just didn't know about all of this work that you guys have done. So maybe in the configuration management portion, you could just list out, hey, these are the documents that we have and that are available. That would be great.
Thank you for your comments.
We still have 2 minutes.
All right. One last question on my part. You did a lot of systems level testing and a lot of discussion about how those tests validated your requirements. I suppose it's more of advice than so much a question, but in the future, I would really like to see more discussion revolving the design of experiments in how you were designing these tests to validate these requirements, not so much just stating that we did so. Was there any consideration towards designing these experiments with the specific outline goal of meeting these requirements, or was it more kind of on the spot?
Not really. We did think about those experiments, how we're going to validate these requirements. A lot of them will be presented in the following presentations because they're from system level below. But a lot of them were, for example, the electronic equipment tests that were pretty straightforward to test the component battery capacity, and those tests that were very straightforward. But we also had other tests like the thrust test for the Vesta system. We actually borrowed a load cell from one of our faculty professors and performing thrust test for each one of these motors. And additionally, we also developed, I'm sorry, probably I should have mentioned all of this offhand, but we also have a validation, I forgot the name of the document, validation plan and validation reports, which is a document that outlines how you're going to take, for example, the battery and measure that it provides the voltage that you require it to do. And then we created a validation report that presents the results of that test. So thank you very much.
I don't really have much more to ask, but I just want to say it's a very good presentation and you've all done a very great job. So I'm proud of that.
Thank you.
Yep, one more? Oh. All right, thank you so much. Our next presentation will start in 15 minutes at 9:15.